Hi everyone, this lesson is about continuous probability density functions. So we saw last time the use of a histogram to approximate this. Now with a histogram, of course, we have to have a certain width for each of the blocks on the histogram chart, and that makes the histogram chunky. They jump up in steps. If we were imagining that the width of each of those little blocks was smaller and smaller and smaller, and we had a very large number of data points in our sample, we would end up with a picture that looked nice and smooth, like this one. And ultimately, if we could find a formula that would describe this curve, we would call that the probability density function. Now, there are two important things that this formula must do. Obviously, it must remain above zero. You cannot have negative probabilities. So the probability function must always be positive in this space. And the other thing is that the total area, not the bit shaded here, but the total area underneath there must equal 1, because that represents the certainty that something underneath one of the possible outcomes must have occurred. Let's take a look at a couple of examples here. Let's look first at this question. Is this function 2x cubed from -1 to 1 a probability distribution function, probability density function? Well, let's just imagine if we pop over onto our graph and we graph that 2x cubed. Now I will limit the domain from -1 to 1. Remember, we can use this notation to limit the domain on our calculator. Let's draw that. There's the graph of 2x cubed. Straight away I notice a problem here. The value of the function is negative. So we will say no. This is not. There's no even need to worry about the second condition. Both must be true. So the answer for this first one is no. The function of x is less than 0. Well, that's all I need to say. That one didn't work. Let's try this one. Is the function of x 3x squared a probability density function between 0 and 1? So let's go back first and we'll take a quick picture. Now, just reuse some of what I've got here. So 0 to 1 this time, and our function is different. Our function was, oh dear, something went wrong. Just take that away. Put 2 there, and our coefficient is 3. That's better. Let's draw that. Let's just move that up a bit. There we go. So from 0 to 1, the function is indeed positive. So far, so good. Now what we need to do is check that the area under that is true. So let's find the area, the integral from 0 to 1 of 3x squared dx. So 3, increase the power to 3, divide by the new power, and our limits are 0 and 1. Obviously the 3 will cancel. I have 1 cubed, take 0 cubed, that's 1. So the answer is yes. That one is a probability density function. Only when we're looking from 0 to 1 though. If we extended the domain, well, the area would get too big and then we'd be wrong. So that's that one. Now, let's try a different style question. What if we were given this function, k times 1 plus x squared, and we know we're working between -2 and 1. We have to find a suitable value for k that will make this a probability density function. Again, both conditions must be true. Let's just think for a minute, if we were to use x of -2. -2 squared will become a positive, so the brackets will be positive, and as long as k is positive, our function will be positive. In fact, it won't matter if x is positive or negative, squaring will always give a positive result here, so this is at least promising. It's always going to be positive if k is a positive number. Let's move to the integration. We want to integrate from negative 2 to 1. Our function is k outside 1 plus x squared dx. And this time I'm going to say that I know the area has to equal 1. So if I bring k to the front of the integral, that makes my integral a little bit less complex. The integral of 1 is x. The integral of x squared is x cubed, and we divide by the new power, and this is between the limit -2 and 1, and just for safekeeping I might move k to the other side of the equation so it doesn't get jumbled up in this. Let's substitute. I would have 1 cubed is 1 over 3 minus -2 plus, now -2 cubed is -8 over 3. All of this equals 1 over k. So 1 plus 1 over 3 is the same as 4 over 3 minus, now if I imagine 2 to be 6 over 3, that's -14 over 3. Obviously the subtracting the negative changes to positive. That's 1 over k. So adding together we would have 18 over 3, and the reciprocal of that is 3 over 18. 3 goes into itself once, 3 goes into 18 6 times. I think k should equal 1 over 6 for this function. Let's just go back to our graphing calculator and we'll try this. Now our domain was from -2 to 1. Or I might just wipe out that whole thing and type it over again. I think k was 1 over 6. And then in the brackets I had 1 plus x squared. So there's my function, there's the domain. Let's enter that. Now draw. There it is. What a lovely little function. Now how will we check? Well, it's clearly it's positive, we can see that. But how will we check that in fact we've got an appropriate area? Oops, sorry. Didn't mean to do that. Should have pressed G-solve. And I can integrate the given function, and I just get to type -2 for the lower bound, then 1 for the upper bound. It shades it in and it tells me there, look, that the area is 1. We knew that because we calculated it. So that's reassuring. There we go. We found that as long as k equaled 1 over 6, we have a probability density function. Now, here's the next idea about this topic. If we were to integrate from the lower limit up to some point, some variable x, this would give me the probability that my random variable was larger than, it was less than or equal to this number here. We call this the cumulative density function. And not surprisingly, the cumulative density function is an integral or a primitive function. So that's a handy thing that we sometimes refer to, the cumulative density function. Now, let's see this in action. We've been told a probability density function for a continuous random variable x is 1 over x squared, as long as x is greater than or equal to 1. Find the cumulative density function. So here we go. The cumulative density function is the integral. Now there it is. It's the integral from the lower limit up to a variable x. The lower limit in this one is 1 up to the variable x of our function, 1 over x squared dx. Well, that's really x to the minus 2. So increasing the power from minus 2 is minus 1 over minus 1. And our limits were x and 1. Substituting, I get negative x to the minus 1 minus negative 1 to the minus 1. So that's really just positive 1 minus 1 over x. That's my primitive function for that that 1 over x squared function. Now, let's take a look at what that really means. If I go back to my graphing calculator, let's take that one away. Let's draw in the probability function 1 over x squared. Now let's do the primitive 1 minus 1 over x. Oh, I forgot to make a note that these were from 1 upwards, weren't they? So, comma, brackets, 1, comma. Now if I want to go forever, I just close the bracket with no entry there, and it automatically works to run to infinity. And same with this one, comma, square brackets, 1, and then close the square brackets. Let's draw them. Let's change the view window a bit. So what if I start with the view window of 0 up to about 12, going in steps of 1 is good. For this one, it didn't go below 0, so let's go from 0 up to, and I think 2 would be plenty there. Let's draw that one. There they are. So the blue line is my probability density function. That's the one where the total area under the blue curve equals 1. And this one is the cumulative density. Notice that it gets closer and closer to 1, but it would never exceed 1. That's 1 minus 1 over x, the red one. Now let's see if we can use that to calculate this. Calculate the probability that x is less or equal to 2. Well, there's two ways we could do that. We could either do the integral from 1 to 2, or we could substitute the number 2 straight into the cumulative function. So the probability that x is less or equal to 2 is exactly, that's the integral from 1 to 2 of my original function. But isn't that just the primitive function of 2? That's why we worked out the primitive function. That's 1 minus 1 over 2, or that's 0.5, 50%. Now, as an exercise, you could do these other ones. The value from 3 to 6, well again, if we had our function that was drawn, remember it went something like this. If there's 3 and there's 6, now we could find the integral from 3 to 6 of our original function, but remember, isn't the primitive function of 3, that's the primitive function of 3, going to tell me that area, and isn't the primitive function of 6, that's the blue area there, that's the primitive function of 6, is going to tell me that area. So wouldn't I be finding it easier if I wanted to have the probability between 3 and 6? I would take the primitive function of 6 and subtract the primitive function of 3. Remember, the primitive function from earlier was 1 minus 1 over x. That's 1 minus 1 over 6, subtract 1 minus 1 over 3. So I'll end up with, what have I got there? 1 minus 1 over 6, that's minus 1, that's plus 1 over 3, that one and that one go. So I end up with 1 over 3 minus this is 1 over 6. That's the answer. Of course, you could have done the original integral and you still would have got the same answer. But that's I think, a bit easier to use the primitive function because we already did the integral, didn't we? And remember, the primitive function tells you the area from the starting point up to some given place. What about this last one? It was probability x is greater than 10. So if I do my little sketch, and let's say that's 10, and we're interested now in the chances that it's greater than 10. Wouldn't my primitive function tell me this area here? That's capital F of 10. So here we go. The probability that x is greater than 10, that's 1 minus the primitive function using 10. Complementary of n. And the primitive function was 1 minus 1 over x. I think you can see that's going to be 1 over 10. So that's a quick little introduction to continuous probability functions, both the probability density function and the cumulative density function. Thanks for watching.